Sorry, people in the video, you missed the spanning tree definition. Okay, so how many people think that 1 is a legal spanning tree? Raise your hand. This graph. Okay, how many people think it's not? Okay. Why? So do we need to add an edge or get rid of an edge? How many people think add an edge to make it a spanning tree? How many people think get rid of an edge? Yeah, so in this case, this is not a legal spanning tree because it has a cycle, right? You can kind of go around the graph. So if we were to just get rid of an edge, now this would be a spanning tree. Okay, what about 2? How many people think 2 is a spanning tree? Raise your hand. How many people think 2 is not a spanning tree? Okay, how many people think not enough edges? How many people think too many? Right, so this one also has the issue of having a cycle. So if we got rid of like this edge, now you have a spanning tree. Okay, what about 3? How many people think this is a spanning tree? How many people, so too many edges? Not enough edges. Yeah. So if we were to add an edge here, then we would suddenly have a connected graph. So before the graph wasn't connected, you couldn't reach every vertex from every other, right? Like these were kind of their own island. So if we added an edge, then you would have a valid minimum spanning tree. Cool. So the correct answer is none. Awesome. So what questions do you have about spanning trees before we get into minimum spanning trees? Okay. So a minimum spanning tree is a spanning tree that has the least total edge weight cost, right? So in this example, this would be the minimum spanning tree for this graph because this is the combination of edges that have the lowest cost that still make up a valid spanning tree. Right, so when we were just talking about spanning trees, we were like, oh, maybe we could include this edge instead of this edge or something. But now with minimum spanning trees, that would be using an edge of weight 8 instead of an edge of weight 4, so we'd no longer have a minimum spanning tree. So why don't you talk with a partner and try to find the minimum spanning trees for this graph? So somebody had a really good question about, with the minimum spanning tree, are we talking about from one point to another point? Because with all of our path searching algorithms, we're always looking for a path between 2 points. So a minimum spanning tree is a graph-wide property. It's not related to any 2 vertices. So a minimum spanning tree always has to do with all the vertices in the graph. It's not between any 2 specific vertices. Does anybody have a minimum spanning tree they want to propose for this graph? Yes.
You could cut out any of the edges that are weight 3 within that box. So if we cut out one from C to E.
Okay, so we can get rid of this one. Okay, and just to make it a little bit clearer, that would be include this edge, this edge, this edge, this edge, and this edge, right? Cool. That's awesome. Does anybody see any other minimum spanning trees? So we got rid of this one. This one. Yeah. Yeah, so we could get rid of this one. So, okay, we'd include these. Okay. Cool. And anybody else? Yes. Yeah, exactly. So, okay. That would be this one, this one, this one, this one, and this one. Exactly. So why is this one not a minimum spanning tree? Where you get rid of B to D. Like that. Yeah, exactly. So this spanning tree is no longer the minimum spanning tree because the total cost is 3 plus 3 plus 3 plus 3 plus 7, which is 19, instead of 3 plus 3 plus 3 plus 1 plus 7, which is 17. Okay, so this works. Humans are really good at this if there are, 6 vertices, 7 edges, that sort of thing. Humans are less good at that when there are hundreds or thousands of vertices and edges. But a guy named Kruskal came up with an algorithm to very quickly find a minimum spanning tree for a graph. Okay. So, and yes, you will be implementing this on your homework. So basically, the way it works is you start off with no edges in your graph. And then we're going to make a priority queue based on edge weight. And then so while the priority queue is not empty, we're going to dequeue an edge. If it connects 2 parts of the graph that are currently unconnected, then we'll include it in our minimum spanning tree. Otherwise, we don't do anything with it. Okay. What questions do you have about that algorithm? We'll do an example too. Yeah.
So after removing all the edges, we should keep them up to the priority.
Yeah, so we aren't necessarily explicit. So the way minimum spanning trees work, we aren't explicitly like removing edges from the graph. Usually how they work is you kind of like return a set of edges that would comprise the minimum spanning tree. But yeah, so generally it's like some sort of like you're looping over all the edges in your graph and adding them to the priority queue. But conceptually we can think about it as there aren't any edges in your graph and you're adding edges back into the graph. Cool, good question. Yeah.
Why do we check if these endpoints are already connected?
So if E's endpoints are already connected, like as an example here, if we were to, if we had included, this edge, this edge, this edge, and this edge, and then we're looking at this edge from D to E now. D to E is already connected, and right, you can go this way to get from D to E. So if we were to connect it this way, we now have a cycle, which breaks the minimum spanning tree. Awesome question. Cool. Okay. So let's do an actual example with Kruskals. So this is the priority queue of edges. I grade them out in the graph so we can visually see like the idea of adding them back in. So does that make sense? So which edge would we look at first? Yep, A1, because it's the lowest cost. So, okay. How many people think include it in our minimum spanning tree? How many people think don't include it? How many people are like still kind of confused about Kruskals? Okay. Yeah, so we want to include it because A1 connects these 2 vertices, this one, and they are not currently connected in our graph. So this has got to be the cheapest way to connect these 2 points. So, okay, so let's include A1. Okay. So our next edge is B2, which is this edge over here. How many people think include it? How many people think don't include it? Okay, yeah, so B2 also connects two edges that are not currently in our graph. Okay, our next edge is C3, which is this one here. How many people think include? How many people think don't include? Okay, cool. Participation is definitely increasing as we go through this. That's awesome. Okay, D4, which is here. Include? Don't include? Okay. E5, which is here. Include? Don't include. Yeah, so if we were to include E5, we would get this cycle between these three nodes here. 1, 2, 3. So we don't want to include E5 in our minimum spanning tree. Okay. F6, include? F6 is here. Include? Don't include. Yeah, so F6 connects this vertex, which is currently unconnected to this whole group. Okay? Here, I'll try to highlight the ones that are currently connected. Okay. G7, which is here to here. Include? Don't include. Yeah. So don't do anything to G7. H8 is here to here. How many people think include? How many people think don't include? Yeah, so here, these two nodes are connected, the ones with the stars, and these 5 nodes with the circles are connected, but they aren't connected to each other. So we do want to include H8 so that we can connect these two groups of nodes. Okay, so now all of these are connected. Then we get I9, which is here to here. How many people think include? Don't include? Okay. J10, which is here. Include? Don't include? Yeah. K11, which is here. Include? Don't include? Cool. L12, which is here. Include? Don't include? Yep. M13, which is here to here. Include? Don't include? Yeah, so if we included M13, we would have a cycle going from like here, 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 and back. So we don't want to include it. Okay. N14, here to here. Include? Don't include? Yep. O15, which is here to here. Include? Don't include? Okay. P16, which is here to here. Include? Don't include? Okay. Do we need to keep going at this point? Are there any nodes not connected? Yeah, so as an optimization, we don't need to like continue going through Q and R because we've already connected all of the nodes in our graph. Yes? Mm-hmm. That's a great question. So the question is like, how are we actually, visually as humans, we can see if things are connected, but how do we do that as a computer? And we'll talk about that in like 5 minutes. Cool. Yeah, so this matches the minimum spanning tree we just got. The total cost of it is 60, which you get by just adding up all the edge weights. Are there any spanning trees of lower cost? Yeah, so this algorithm finds the minimum spanning tree, so there wouldn't be any of lower cost. There are also, so is there a spanning tree of equal cost for this graph? How many people think yes? How many people think no? Yeah, so for this particular graph, you won't have there's only one minimum spanning tree because all of the edge weights are unique. In that first example here, we saw that there are multiple minimum spanning trees because there were 3 edges with cost 3. So we could use any 2 of those 3 edges. But here, since all of the edge weights are distinct, you're only going to have one minimum spanning tree. Here's another example. This is from Wikipedia, just kind of showing like, oh, we have a cycle, so you don't want to include this edge. And then here, we found our minimum spanning tree. Okay. So back to your question. How are we actually going to implement cruise goals? Because as humans, like, we did really well, but how can we actually implement it ourselves? One big thing is, so we're using a priority queue. So you thought assignment 5 was hard and like, it's all coming back. Huffman, this assignment, priority queues are great. And then we also need to talk about how we can figure out if the two vertices that are the endpoints of the edge are already connected in our graph. Okay. So a good way to conceptualize this is we're going to have different clusters of vertices. So originally you saw how I was like labeling some of them with circles and some of them with stars, and the stars and the circles weren't connected. That was like kind of my way of trying to represent these clusters of which vertices are connected. So the idea is you'll have these clusters, and as you'll need to be able to merge these clusters as you add edges to your minimum spanning tree. And you also need to very quickly be able to determine if the two endpoints of an edge are in the same cluster or not. There are lots of ways to do this. I would encourage you to think about it because you'll have to implement this on your homework. So I'm not explicitly answering your question, sorry. But this is a really good kind of mental model. So maybe think about some data structures or techniques that we've learned about this quarter to implement this. Yeah. Oh, sorry. Yeah. Yeah, so basically the idea is as you add edges, you want to consider edges that are, nodes that are connected to each other as part of the same cluster. So I was representing that in our example that we just walked through by putting like stars on some of the vertices and circles on the others. You might like actually draw it out like this, where they're actually connected in like the same group. Yeah. Okay, so the question is like, why do we need a minimum spanning tree? Like we just talked about this for 20 minutes. This is, yeah. They're used to make mazes, which is cool. They're also, more importantly, used to like do things like power lines, that sort of thing, where you need to connect large areas and you want to do so in the like least cost way possible. So you don't want to like, an example might be you want everybody in the country to be able to like access all other parts of the country, but you don't want to build a bunch of redundant roads because you have like a finite road budget. So you'd want a minimum spanning tree connecting the cities of your country. Cool, great question. Does anybody else have any other examples of where they think a minimum spanning tree would be good in real life? I think to some extent you might get some of that with not necessarily a minimum spanning tree, but like new airlines might try to do a minimum spanning tree with like flight paths, because it's more important that you can just like connect two places, and then like as airlines get bigger, they'll start adding cycles, right? Cool. Okay. Great. Any last questions about cruise goals before we move into graph implementation? So, like I said, a graph is a data structure. So we've been talking a lot about how we implement different data structures. So let's talk about how we'll implement a graph. So the idea is we had talked about graphs store vertices and edges. So you need some way to represent these vertices and edges in memory and to have good ways of like looking them up or having access to them, right? So we're going to see 3 different potential implementations of a graph. And some good questions to think about is, like, what would happen if you wanted to add an edge? What would happen if you wanted to add a vertex? What would happen if you're trying to search for a particular edge? If you're trying to find the neighbors of a node? that sort of thing. So the big thing that is good to remember is that it depends on your, it depends which implementation that you want to use based on what you're trying to do with your graph. Okay, so also maybe try to think about which implementations would be best for the different algorithms that we've been learning. Okay. So the first one is probably the easiest one to code. It's just, let's keep a list of all the edges in our graph. So we aren't even like explicitly storing vertices. We'll just remember, like, oh, if this one is edge AB, that means that there has to be vertices A and B in our graph. So how fast would it be to figure out if how would we figure out if there's an edge in our graph? Like if an edge exists between A and D, for example. Yeah. Yeah, so it's an O of N operation because you have to go through all of the edges in the graph. And sometimes when we're talking about graphs, we'll talk about like O of E versus O of V. O of E for the number of edges and O of V for the number of vertices. But you're exactly right. Like, yeah, just to figure out if there's an edge in our graph, we have to look at all of the edges in the graph. What if we want to find like all the neighbors of a given vertex? What's the cost of doing that? So the question is like if we want to find all the vertices or all of the, you said O of V times E. Does that mean like for every vertex we need to go through the whole edge list? So that'd be good if we want to find like all of the neighbors of all of the vertices. But if we just want to find one vertex's neighbor, it'd just be O of E. So you can just like look through the edge list once. But yeah, that's exactly right thinking. So okay. Basically the moral of the story is with an edge list, you have to iterate through the entire list for basically any operation that you want to do. So, not super great, right? Like one could think like, maybe there's something better than like having to keep on looking through our entire data structure every time. However, there are some advantages of edge lists. They're really easy to implement. They're really easy to do for each loops over edges. And they're also really easy to add vertices to, right? Like if I were to just draw a vertex here, call this H, I don't need to change my edge list at all because there aren't any edges connecting to H. So, okay, let's get a little bit more specialized. So instead of just storing all the edges, why don't we store all the vertices and have each vertex and know for each vertex all of the neighbors, right? So we're like basically storing all the edges for every vertex. So what are some operations that you think would be better than the edge list operation? Yeah. Yeah, so this is really good at finding, the neighbors for a given vertex. Like you just go and you find that vertex in your data structure and look, here's like the full list of all of the neighbors. So that's really good. What else might be good? Or is there anything that's worse? Yeah.
When you're storing it into the list, are you storing them in order or not in order?
So the question is when you're storing the vertices into your list here, are they in order or not in order? Basically, so you might not have an order to your vertices. Like these are just letters. You can imagine that they're actual strings, which aren't really ordered. So you don't necessarily have an order here. And in fact, we'll talk about how we would actually implement this. But usually you'd use like a map for example, or set. It's like, is it easy to add a vertex to this graph? Yes, no. So if we were to add H here, what would need to change about our representation? Yeah? Yeah. Yeah, so exactly. So when we add H here, we would need to just add it to the end of our adjacency list. If we wanted to add an edge, you're right. We would need to like add here. We need to say like, okay, this points to D, and D includes H. So okay, that's also like kind of one cost, right? So with our edge list, we weren't storing, like if we stored BC, we didn't store CB. But this one, we would need to store both ways. So we have to store like twice as much information. So that's another potential cost. Basically, it's really good at adding new vertices and edges to the graph, right? It didn't take that, it was a constant amount of time. And it was also very good at finding neighbors of a given vertex. The thing it was worse at is it's hard to determine whether a given edge exists, right? Because in order to do that, we have to go through all of the neighbors for that vertex, right? So if we're looking for AG, we'd have to start off here and be like, okay, is B what we're looking for? Is D what we're looking for? Is G what we're looking for? So we'd have to go through the entire list. What questions do you have about adjacency lists and edge lists so far? Yeah.
Why does D include itself?
That was a typo, and I'm sorry. Yeah, this should not be here. Sorry. So, okay. Now there's a third kind called an adjacency matrix. And so the way that works is you have like the vertex on either side, right? And so you would basically put like a 1 if there's an edge between two nodes and a 0 if there's not. And it's diagonally symmetric because if there's an edge from A to B, then there's also an edge from B to A with undirected graphs. Okay? So what is this one good at or bad at in terms of operations that we've talked about? Yeah. Yeah, so it's really bad at adding new vertices because like let's say, so we added our H down here, all of a sudden now we have to like add this whole extra column and row here. Darn, I can't draw on the black, but there's an extra column here, right? And you'd have to fill it in with all these zeros. So that's actually like a very costly operation. And because you generally can't, like if it were an actual grid, you'd have to, copy everything over. So exactly, so it's really bad at that. What about finding neighbors? Is it good at that? Yeah, so it's like kind of okay. So in order to find all the neighbors for a node or for a vertex, we'd have to go to that row. Like if we're trying to find all the neighbors of C, we'd go here and we'd have to look at all of the different vertices to see if there's an edge between them. So this is a major improvement over our edge list because our edge list, we had to go through the entire list of edges, which is a lot, right? That's O of E. In this case, we only have to go through all the vertices. But that's still not great because like with our adjacency list, we just needed to go through the actual list of neighbors, which is basically as good as it gets, right? So this one's kind of medium at that. What about finding if an edge exists in the graph? It's like before you're trying to find, if G is a neighbor of A. So good at that, bad at that. So how many people think that this is a good data structure for doing that? How many people think like kind of meh, like in between edge list and adjacency list? How many people think worse than edge list and adjacency list? Yeah, so it's actually really good at that because in order to find if A and G are neighbors, you just go, okay, like you can go right to this spot and look at this and look and see like, oh, there's a 1, therefore they're neighbors, right? So that's an O of 1 operation. Yeah, the other big disadvantage of adjacency matrices is that you have to store all of this information, right? So if you have like thousands of nodes, but you only have like one edge for every node on average, you're going to end up with a lot of zeros in your graph. So that's a lot of extra wasted space. Do you all have any questions about like the differences and the costs between these different implementations, or why you'd use one over another? Yeah. Mm-hmm. Yeah. Cool. Good question. So the question is like, how would you store the weight? So with our matrix, we could just directly put the weights in here instead of like zeros or ones. But how would you do it for the other ones? So for edge list, you can have that weight be like a field in your edge structure, right? So the edge has 2 vertices, a start and an end, and a weight. For the adjacency list, you'd have to store that as an extra field as well. So it is more like it's higher cost to add weights to adjacency lists and edges and the edge list than it is to add it to the adjacency matrix. And then if you have directed graphs, you lose that nice diagonal property because you no longer have the guarantee that like if A has an edge to B, then B has an edge to A. So here we see like, oh, there is an edge from A to B, but not from B to A. So those are the big differences when you're talking about weighted and directed graphs. Okay. Let's say we want to implement breadth first search. So we have 3 options, right? We have our edge list, our adjacency list, and our adjacency matrix. How many people think that edge list is the best way to implement breadth first search? Actually, if this helps. How many people think the adjacency list is the best way? How many people think the adjacency matrix is the best way? Okay, let's start over. That's 0 participation. Okay, so this chart is basically just shows like kind of the costs and trade-offs of each of these different implementations. Like there's not one that's just universally better, right? So this kind of goes back to it depends on what you're doing. So the stuff that's green is like kind of the winner in that operation, and the stuff that's red is the loser, right? So adding a vertex is best in edge lists and adjacency lists and worse in adjacency matrix. So for breadth first search, do you all kind of remember that from last week? Sort of. That's the one with the Q? Yeah, okay. What do you all think would be the best data structure to use that? Does anybody want to like volunteer an answer? Yeah. Yeah, so an adjacency list is really good for breadth first search because you have that step of like for each neighbor of the vertex and queue it into your queue, right? So that's really good for adjacency lists because it's only the number of neighbors instead of like the number of vertices or the number of edges. What about Kruskal's algorithm? Does anybody have any ideas of which one they think would be best for that? Yeah, so for Kruskal's, an adjacency list is good because you need to go through all of the edges of your graph. So if you wanted to do that for the adjacency matrix, you'd have to go through like v squared, versus for the adjacency list or the edge list, it's only of the number of edges. So really, I mean, it actually kind of depends on what you want to do with your graph. So if you're ever asked in an interview, like, hey, can you implement a graph? The first thing you should ask is like, what do you want to do with this graph? Because it depends. Okay. Do you all want to see how we've implemented the graph? Like how we made that choice? So this is graph.h, which is basically what basic graph is based off of. So here we have a set of nodes and a set of edges. So this set of edges is basically like that edge list that we were talking about, but then we're also storing our nodes. And the idea behind this is when you go to basic graph, which is here, vertex gen. Sorry, hold on. Vertex. Basically, when you go to, when you go and look at a vertex, you'll see that it has if you look at a vertex, you'll see that it has a list of edges associated with it. So basically what that means is if you go back to graph and you want to see if two points are connected, you actually go through and have to go through like all of the edges in that vertex. So it's actually sort of this hybrid edge list, adjacency list approach, because you have this set of edges, so it's really easy to get all the edges in the graph, which is really good for cruise goals. And then also you have an adjacency list, so that's easy to find the neighbors, because the other big thing that we're having you do is do all the pathfinding algorithms, right? And so like you can actually see, okay, here we have, you know, we're actually having to go through that whole list of neighbors just to find if two edges are connected. So that's kind of the trade-off that we made based on knowing the assignment that we'd have you all do. Earlier, somebody had asked, like, are these stored in order, and how does that work? Basically, you wouldn't have them stored in order because there's not necessarily an order to your vertices. It depends on the type that they store, like the way that they're named. So generally, you would have some sort of like map of vertices to like a list of edges, or you would just store the collection of edges inside each vertex, which is what we did in our implementation for adjacency list. And then for the adjacency matrix, you would generally have a map instead of like an actual grid. Do you all have any questions about the implementations, the trade-offs between them when you would use each one? Yeah. Is edge an object? So edge is actually a struct. In our example, you could make it an object, like a class. Yeah, generally it makes more sense to make it a struct because there aren't necessarily methods that would be, like, you need to be able to access all of the fields of it pretty easily, so that's why it's generally a struct. Yeah. Yeah, so hold on. Let me see if I can pull it up. Trailblazers. This is your code. So edge. Okay. So yeah, you can see that for each edge, there's like a start vertex and a finish vertex. This is just like, you can call the finish either finish or end. And then it also stores like a weight, like we talked about for our weighted graphs. And then if you want to see vertex, that's this. So there's like the name of the vertex, and then the set of edges that lead out from that vertex. So that's the way that you can get the neighbors really easily, is you just go through each of those edges and then find the endpoint of that edge. Actually, I guess these are both classes to answer your question. So they are classes. So the question is, do you use arcs or edges? This trick is it gives it an alias is the official term. It's like a nickname. So you can use either arcs or edges, and they are exactly equivalent. It returns the same thing. We do that because like sometimes people will forget what they're called. We also do something similar for vector, where we include size and length as a method because nobody wants to remember if vector has a size method or a length method. Great question. Any other questions? Okay, have fun on Trailblazer. And what'd you say?